So it's been frustrating for like the past 100 years, if not longer, but really within the past 100 years, is that academia and government, big institutions have been operating within um, scientific disciplines in which you could say empirical rigor is paramount, but the foundational premise of their physical sciences, the globe, for example, has been basically a triumph of mathematical underdeterminism, model fitting, data fitting, back testing, you know, a a practice in the study of signs and symbols, which is semiotics, and not really concerned with objective measurement. And there's so many fallacies, so many ad hoc rescue devices that have been attached to this globe in order to continually rescue it and make it work and allow other scientists to use the globe and to backfit their data to it. It's all circular reasoning. It really is. And I really think it begins with the fable of Eratosthenes, the gigantic circular myth and tautology that Eratosthenes had given us. Seems to be the go-to, right? Whenever we ask someone for proof of the globe, it's always back to Eratosthenes, a man that may have never existed. Um, so that narrative goes back to when was that, like 200, 300 BC, maybe 250 BC, split the baby. So Eratosthenes basically said that he measured a 7.2 degree shadow. um, 7.2 degree shadow uh, difference, actually, a shadow angle difference of 7.2 degrees between two places, Syene and Alexandria. These are two places that he thought resided along the same longitudinal meridian, and there was a 7.2 degree shadow difference between the two. And we're told that this difference of angle, 7.2 degrees, proved the curvature of the Earth. And ultimately, what this was an exercise in was begging the question, petitio principii. And if we're using a shadow as a proxy for curvature, then we have to inject some kind of assumptions. We have to inject some kind of parallel ray assumptions if we believe in a globe, because that's how you're going to get a globe. You're going to have to assume parallel rays. And the reason why you're measuring angle divergence is not because you're looking at a small object from two different vantage points. No, that's not what the globe says, folks. It says something that is completely unintuitive. It says that you're looking at one gigantic object whose light rays are not fanning out like spokes on a bicycle wheel, but rather that light is coming to you and everybody that can see it in parallel. So where do you get the 7.2 degree shadow divergence? Well, we get that by assuming parallel light is casting diverging shadows on a curving surface, and the curve curves 7.2 degrees from one place to another. And that curve of the surface that the shadow is being cast upon is what's different. But you can have different shadow lengths on a flat surface. It is not cast by a sun giving off parallel light, but rather a sun that is giving off radially splaying out diverging light, as you would typically expect from a source like a candle or a spotlight or a campfire. So if you use like a shadow as a proxy for curvature, you're going to have to inject some assumptions. And when you do that, that's backfitting, that's data fitting, that's begging the question. It's an exercise of underdeterminism in modeling. If you take the same exact angular data, but you strip away all those assumptions of parallel rays and apply it instead to a flat plane, The math resolves perfectly to triangulate a local sun above the Earth. Now, you will not be able to get its fixed position from multiple observers simultaneously, but that's not exclusive to a flat Earth. That problem also exists amongst globers. They can't triangulate the position of the sun either. So when they say, well, you flat earther, you have a problem, because if you get three simultaneous observers to triangulate the sun's height above the Earth, you can't do it. You can't triangulate it. Well, you can laugh and say, I know you can't. I know you can't either. You can't either. You can't either. Nobody can. Nobody can triangulate the height of this or the height of anything in the sky. It's a celestial body. Nobody can. You can't triangulate the height of an object that is casting parallel rays to a curving surface. So it's not quite the gotcha that they think it is, because they have the same problem. We all do. We're all in the same boat together. So if you go back to Friedrich Robert Helmert, F.R. Helmert, the father of modern higher geodetic surveying, Helmert, yes, the guy who wrote the textbook on how to survey the globe in the late 1800s. Helmert, whose two-volume set spans nearly 1,000 pages, written in German, translated into English, French, Spanish, multiple major languages, but not every major language. His two-volume set is quite honest in how it describes the physical surface of the Earth. I mean, Helmert actually openly admits that the physical surface of the Earth is irregular and follows a complicated law of formation. Um, he admits that they're not actually measuring a globe, and nobody does today either. They measure local angles and local distances without the globe, and then mathematically reduce. That's their word. They perform a reduction. Kind of like imagine if you could take a blanket, you and a friend, and you spread out the blanket and you hold it flat between you two. And then both of you lower that blanket down onto a basketball. You are reducing the horizontal datum to a globe model. You're reducing the flat Earth measurements that you took that went into your data, and you use math to bend it and wrap it around a ball. So when we say the horizontal reduction of the datum, or the reduction of the horizontal datum, or the reduction of a datum to the globe, or to WGS 84 or some model, the reduction part is what's interesting. It's the word reduction. They are lowering, they're reducing, they're taking something that they measured flat and they're allowing it to rest upon a curving surface mathematically. That's what they're describing. Geodetic surveyors don't actually measure, they mathematically reduce. They measure local angles and then reduce those observations to a theoretical construct called the reference ellipsoid. So, and the fun part is you can choose which reference ellipsoid you. That's right. So you're taking your real world observations and you get to pick any theoretical model of the Earth that you want to reduce those to. You can reduce it to a 1920s version of the globe, or a 1980s version, or an 1860s version of the globe, or any version of the globe that you want, or a flat surface that's not a globe, or a lunar surface that's not a globe. You can make it a dinosaur nugget, a banana, donut, doesn't matter. You can reduce your measurements to any topology. So, and Helmert acknowledges that a topology reference is chosen for computational convenience. Then you're performing backfitting. You are doing data fitting. You're back testing and affirming the consequent. That's begging the question. What happens when your instruments do not orient or align themselves to the vector of gravitational acceleration and buoyant acceleration? What happens when your instruments aren't aligning with plumb? How would you figure that out? Well, your plumb line, is that set by something in reality, or is that set by something mathematically with a model? No, your plumb line is absolutely set in reality. But the problem is, if you were to choose a way to represent the Earth with a lumpy geoid, and then you were to go take a physical plumb line measurement, and it doesn't match that lumpy geoid, what's true? What's true in this case? Your measurement in reality or the model you picked? What happens when they don't match? Well, guess what? They actually don't match. And geodetic surveyors call this, in this case, a deflection of the vertical when your plumb line doesn't match with the mathematical model. Well, how do they determine that in more detail? Well, they measure a discrepancy between the hanging plumb line and their geometric fiction, and they apply mathematical corrections to force reality into the fiction. They open up a nautical or astronomical almanac, because geodetic surveying combines astronomy with civil engineering. You open a nautical almanac, and it says basically, we think Earth is a globe, and if Earth is a globe, then at this particular point in time, let's say 2:31 a.m. at 43 degrees north latitude and 174 degrees west longitude, that, I don't know, a star, call it Pop Tart 5. The star called Pop Tart 5 will be directly overhead at 2:41 a.m. Boom. At this particular point in time. They open their autumn almanac and they look at that and they note the time. They're like, wow, so for hundreds of years, people have recorded this particular star, Pop Tart 5, to be at this location at this point in time. Well, I'm in this location. I'm not exactly at the location where the almanac would present, but I I could probably deduce or derive my location. So let me go do that. So I'm going to go derive my location, and I'm going to say, oh, shoot, I'm off by a few arc seconds or arc minutes. Crap, what happened? My plumb line. If I was directly underneath that star, it would not be directly under that star. What happened? How come my almanac is off by the plumb line that I set? Well, at this point I have two choices to make. I can either doubt my measurement or doubt the almanac. Maybe I could opt for a third and doubt both, in which case I'd be really skeptical. And I may as well do that. It's within my rights. But let's say I doubt both. Or what if I only doubt one? What if I'm a modern geodetic surveyor and I say, you know what? My plumb line, my physical plumb line is what's wrong. So when I open this astronomical almanac, this one is correct. Yes, this model that I'm referring to is the correct one. Because why would hundreds of years of observations all be wrong? And I may be a geodetic surveyor, but I don't really know for sure how the history of astronomy was poured into this almanac. I have an idea, but you know what? I'm going to accept this as ground level truth. My plumb line, it's slightly inaccurate. So how do I deal with this? Well, I'm going to apply a correction. That's right. I'm going to apply a correction. And I know I measured my plumb line 50 times and it's still wrong according to the math and according to the model that it should match. And it doesn't match the astronomical models. So yeah, the model's correct because that's a globe and my plumb line. is not correct, even though I can measure it accurately, and other people can measure it this way too. But everybody's wrong. The model is what's correct. That's exactly what they're saying, folks. They're saying that their instrumentation is wrong. The model is correct. So the ad hoc rescue comes in. So what happens when empirical reality violently contradicts the globe model? The survey, the Great Trigonometrical Survey of India, I think it was called. Remember people talking about that? Surveyors found that the massive Himalayan mountain range, massive mountain range, did not deflect the plumb line as much as Newtonian physics predicted, as much as Cavendish would have wanted. Yeah, that's interesting. The idea is that the gravity must be pulling starlight in local areas in such a ways to deflect away from what is expected with your measurements. So when you hang a plumb line, Pop-Tart 5, the star we referenced earlier, should be at a particular position in the sky as you hang your plumb line relative to what the plumb is pointing to in the sky. And for simplification purposes, let's say you were at 2:41 a.m. at what did I say? 43 degrees west or north latitude, and was it 170 degrees west longitude? And let's say you're there at 2:41 a.m. Planet Pop-Tart 5 should be 90 degrees zenith to your position, and you string a plumb line, and it's not. They say that gravity is bending the starlight such that your plumb line doesn't match. Yeah, so the gravity is deflecting the plumb line. It has to be, guys, because the star isn't completely overhead as you expect, but the star must really be there and gravity's warping it, which means it must really be straight, even though it doesn't look that way. So when they take their pendulums and they take their dowsing rods, they start swinging their pendulums and tensing their dowsing rods around the Himalayan mountains, and they find that, for some reason, plumb lines are way more accurate here. I can get much better accuracy relative to the astronomical almanac than I thought I could. Maybe Isaac Newton was wrong. These mountains should be deflecting a whole ton of starlight. I should be completely inaccurate with my plumb lines relative to the astronomical almanac, but I am so accurate this hurts. So what's happening here? Is Isaac Newton wrong? Well, they say no, they're going to keep Isaac Newton. They're going to keep the globe from the nautical almanac, but they're going to say that the Himalayan mountains aren't as deep, aren't as massive. They're not bending the starlight as much as you would expect in that local location. For whatever reason, they're going to say that the base of the Himalayas are probably not as dense. They don't extend as far deep into the earth as they thought it did. And so they're going to update their model. So instead of basically falsifying the gravity model of Newton, two surveyors, George Bedell Airy and his friend Pratt, they invented a term called isostasy. So they hypothesized that the mountains possess some unobservable low density roots that are extending deep into the mantle, which would normally cancel out the gravitational pull that they expected based off of Newton's model. The observed terrain failed the math, or did the math fail? They invented unseeable terrain to save the theory, folks. George Bedell Airy invented unseeable terrain to save the theory because gravity didn't pull like they expected to in the Himalayas if Earth is a globe. That's a huge fudge factor, isn't it? I mean, you can smooth out anomalies all day long with your theory. You can keep your theory, no matter how false it is. And when a surveyor measures a physical flat baseline distance on the ground, in geodesy, that empirical measurement off the bat is deemed invalid because it has to undergo this reduction. So there's like a difference between geoid height and ellipsoid height called orthometric height. Both of these are unseen. Both of these are unseen corrections, and both are applied. The empirical ground data that they measure is erased and mathematically replaced in order to allow their convictions to testify for a sphere. So if you understand the difference between raw data and theoretical frameworks that are used to interpret the raw data, then you have to realize that the globe is basically an object from representational reality, not even representational, from imagined reality. It's not even a simulacrum. It's a conception that generates its own reality. And furthermore, as we keep pointing out, the map preceded the territory. The globe preceded flat Earth as an idea. The globe has been legislated and mathematically imposed and not measured. And it's okay to be skeptical of this entire process. It's okay. It's okay to say that it's crazier to think that the world could be delusional with the globe than it is to accept the reality of a flat Earth measurement that you can go obtain and justify on your own. That's right. So you can be a skeptic, and in the process, you're not rejecting science. Not at all. You are part of the process. You're part of the demand by science, just to anthropomorphize science a bit. Science is demanding your skepticism. Science is demanding your purity of your epistemology. I can't even say it. Epistemology. The way that you arrive at how you know something to be true is what the scientific community, if it even is a community, is demanding. They want to see that. They want to see that documented. They want to be able to verify and replicate it themselves. So yeah, you can be skeptical. And in the process, you're fulfilling that need. Just don't go doing the same things that got us here in the first place. Don't go mathematically underdetermining your way to flat Earth. Models are not reality. Benchmark your claims to reality, not models. The map is not the territory. All maps are imperfect. All projections are wrong. But the question is, how wrong? All distances on maps are inaccurate. The question is, how inaccurate? All orientations of things on maps are inaccurate. The question is, how inaccurate? What is the true distance between New York and Paris? How do you measure that? What is the true orientation of New York with respect to Paris? And then how do you actually measure that? Yes, it is 2026. We've not actually measured these things at all. We've created maps and we've calculated them, but we don't know for sure how far these cities are or what their true orientation with respect to each other actually is. It may be pretty close. current maps, WGS 84 and all that may be pretty close. But what I want to know how far apart are they from reality? As a flat earther, I want to know exactly how inaccurate latitude and longitude on WGS 84 actually is. How do I go do that? How do I determine how inaccurate this is? Well, I'll tell you what, I can't use WGS 84 to determine how inaccurate WGS 84 is, right? That'd just be fruitless effort, fruitless endeavor, and circularity. And it also doesn't do me any good to assume that the Earth is a globe of a different latitude, longitude, a different conformal shape. Like, I'm not going to use instead WGS 83 and compare that to WGS 84 and say, oh, WGS 84 is more accurate because it's newer. No. What are the actual measured distances between things? What is their actual orientation amongst these things? We don't really know. We know enough to question the prevailing theory, the prevailing belief system of a globe. We definitely know enough. We in our community have done laser measurements, have done long distance observations of all kinds. We've got our own surveyors, our own people with theodolites, our own people with high-tech long-distance super zoom cameras and airplanes and weather balloons. We've got all these flat earthers who are totally decked out with all this tech. We know we've measured the Earth flat. The problem is how is that reconciled with WGS 84, with latitude and longitude? We know that so-called error corrections are baked into a continuously updated GPS system. How much of those corrections flatten out the Earth again? How much of those corrections actually diverge from the ideal WGS 84? What kind of corrections are we talking about? Ionospheric negative refraction of radio propagation corrections, like all kinds of crazy crap, timing corrections. Oh, the ionosphere was thicker, at this point in time, so we had to extend our pseudo-ranging packet by an extra 0.0235 milliseconds. I mean, that's the kind of stuff that goes on. Oh, you're on a geoid, you're at this particular lat long, so you're vertical, your gravity vector is deflecting and pushed off to the side a bit. So we're gonna correct that. And at every point between the 5,000 miles from point A to B that you traveled, we're actually going to update your path incrementally. So while we'll show you WGS 84 and we'll show you your path on a mathematical globe from A to B, your actual path was corrected continuously along the way. Where did that actually bring you? Who the hell knows? GPS isn't actually measuring your distance, isn't actually measuring your true orientation and your true reckoning. No, it's internally consistent within the system itself. So as long as you stay within like WGS 84, within GPS, within this framework, this interoperable framework of the modern world, then you'll be self-confirming your distances and orientations and your time to travel between locations all day long. And you'll be able to say, you know what, I'm using the globe and I'm fine with that. But we're not fine with that. We're not fine with that because we've measured errors in the globe, irrefutable errors. So we want to know just how far off we are with all this. I don't know if we'll ever get that answer. I mean, to get that answer, you need to fund massive expeditions of the likes that haven't been seen in 100 years or longer. I mean, nobody's done any of these explorations in over 100 years, right? I mean, the last great exploration was probably Admiral Byrd's so-called exploration of Antarctica, if you believe any of that. Why wouldn't I believe Admiral Byrd? Yeah, I mean, don't we have many flat earthers who do? Maybe that can lead me to the next question. Why should we trust Admiral Byrd? Hmm. An open Freemason? I mean, not that you want to throw babies out with bathwater, but why should we trust Admiral Byrd? Wasn't there some controversy regarding a North Pole expedition of his? Yeah, 1926. Los Angeles Times. Los Angeles Times writes in 1996, new clues add doubt to Admiral Byrd's claim of North Pole primacy. That's right. 1926, it's claimed that Admiral Byrd actually reached the North Pole. Amazing for Western prestige. But it looks like he might have been deceptive about that. And this Los Angeles Times article doubting Admiral Byrd's claim of the North Pole primacy, it reads, again, this is May 9th, 1996. Richard E. Byrd, the famed American polar explorer who claimed in 1926 to have been the first person to fly over the North Pole, may actually have turned back 2 hours and 150 miles short of his goal, according to new evidence released by Ohio State University's Byrd Polar Research Institute. Yeah. There was this era leading up into the third geophysical year where everybody, for a couple hundred years, from America to Russia and France and England, were racing to make all these scientific discoveries about our world.
Was that due to the GPS giving errors back then?
Mhm. As long as you use GPS consistently, you're going to be okay.
Yeah, GPS works great if you're on flat land or on a hill, but if you're in a valley, all of a sudden GPS doesn't work so well.
I know, right?
I guess the satellites over my head don't work.